So Uber have been stalwarts of this conference, but I think it's the first time that Divya and Xuan have talked at this event, if I'm not mistaken. Divya Nagar is a software engineer in the feature engine team at Uber, where she leads the development of the feature store, the data plane, powering embedding use cases across both generative AI and core ML applications. Her work focuses on designing and building scalable, reliable, and high-performance architecture for feature and vector stores, and she's passionate about creating seamless production-ready solutions that accelerate machine learning and AI development for engineers across Uber. You can start sharing your screen, and then I'll introduce Yuan while we get getting up and running. And Zhuan Feng is a software engineer at Uber's feature store team based in Sunnyvale, and has around 3 years of experience working in various teams, including feature ETL pipelines, transformations for features, RAG, vector stores, and all the cool stuff. Over to you. I think we're looking good, Divya. Floor is yours.
Nice. So we can start. So today we would be presenting Vector Store. So this is Uber's embedding platform. We will go into the details of how we started with it, why do we need it to begin with, and what all things we have right now. So the agenda for today's talk is primarily what is it, what is our vision behind it, how it differs from the traditional feature store we already have at Uber, what different data sources, how do we ingest the data, how the retrieval works, how are we managing the data versioning and everything. So what is Vector Store? So a vector store is a centralized system for managing the embedding datasets. We provide the ingestion, retrieval, metadata management. We use it extensively in our generative AI applications across Uber. And as well as we have a lot of use cases with the core ML, let's say Uber Eats search and other different models which use embeddings. So why do we need a vector store? So to build out some differences between the feature store and vector store, we'll start looking at the data and model. So if we talk about feature stores, you usually have your data layer and your model layer. So your data layer and model layer, they mostly operate independently. You have data processing, data ingestion, data serving. Once your data is ready, then you would start with model training, model inference, and model serving. So they are loosely coupled. They mostly have independent operations. Data pipelines, they don't really need to have inference or anything, or they don't really need to have all these details. So they can pretty much operate independently, have their own versioning systems, a very loose coupling. But when embeddings come into picture, these two layers kind of start mixing with each other. So the way you usually work is you would have some embedding model. So it may happen that you train your own embedding model using the standard feature store, or you may be using some standard embedding model which are available in open source, like provided by OpenAI, Gemini, and other standard models. So the way your flow of the end-to-end pipeline, the way it looks like is this. So you train your model, then you would process your data. The data processing is also slightly different. Like you have chunking, we have some custom processing. You might want to process this textual information. Then once you process your raw data, you would generate the embeddings. And that's where your model inference kind of starts coming into your data pipeline. Once your inference is done, you would do your data ingestion. You may ingest it to Hive, you may ingest it to other vector database. And once all these things are ready, then you would do model serving. And even at the serving time, there are usually more than one model involved. The one which first used to generate the data, and the second model which is actually used for the training and serving. So the coupling between data and model becomes very tight. You have coupled versioning, and then now you have to manage all these model dependency in your data pipeline. So that is one major difference. The second major difference comes in the way we treat the data sources and the way your lookup works. So when embeddings comes into play, your data and so apart from this coupling, the data and the retrieval is also pretty different. In case of feature store, you have structured tabular data. You usually use aggregations or time series features, near real-time features. Your lookups are mostly pointed lookups. You would look for a specific join keys or UUIDs. In case of offline, you would usually join features like we have seen with Chronon and Tecton or all other open source features. They provide aggregation and joins. But in case of embedding and in case of semantic search, most of your data is unstructured. You have knowledge bases, you have wikis, you have code repositories which you want to generate embeddings on. So your data processing is very different. Apart from that, your search or your retrieval changes. Instead of point-in-time lookups, you have semantic retrieval. You would use your KNN or maybe ANN algorithm or some sort of optimizations to do the search. So given all these very heavy differences, it is pretty hard to kind of merge these two things as part of feature store. So we decided to build this parallel system, which is owned by the team. However, we have slight differences. So the idea and the vision behind Vector Store is building this unified data platform, which can instead standardize all the ingestion and processing, designing this plugin based system where people can come, they can all the different data sources across Uber, we can put all these plugins, they can easily process this data. Then the embedding generation, we design new data pipelines which can support embedding generation. Then the last next part is usually how do we make sure that your model management is handled by default with the platform. So handling all this data and model version compatibility, and then providing the serving layer. Like at the time of serving, the user need to make sure that they use the same embedding model which they use to generate the data. And the platform provides these capabilities and libraries which will take care of all of these things. So this is pretty much the idea behind Vector Store. Now we will do a deep dive into the ingestion, serving, and all other aspects of it. So this is our ingestion pipeline. If you talk about the traditional feature store, usually your ingestion pipeline would look pretty much very similar, except some differences like in terms of sources and processing and embedding generation. The ingestion part pretty much remains very, very similar. So what is this ingestion pipeline? So this ingestion pipeline is a batch platform pipelines. So the way it works is the first phase is loading the data. So we have designed a plugin based system where some of these data sources are contributed by us, but we also have people across Uber contributing to this these pipelines and the platform. So right now, for example, we have in Wiki, you can use Slack, messages. You would want your messages to be processed and embed for your RAG applications. You can use Google Drive, Google Docs, Files, Stack Overflow, all different type of sources. So you basically provide the configuration. Then we support different type of data processing. We have different chunking strategies available, so you can just configure them. In a lot of cases, it can happen that you want to do some custom processing. Like instead of chunking the data, you want to just whitelist or allow list certain keywords. So those kind of processing, you can write your own custom code, and then you can use the pipeline to use that custom code to do custom processing. Once all the data is processed, the next phase is embedding generation. So right now we support some open source models. So here we have put a reference of GenAI gateway. We have at the end of this presentation, we have attached all the inch blogs and the information of the components we have used here. So the GenAI gateway blog is attached if you want to look for the references. But we basically support all these open source models. But if you have any in-house fine-tuned model on the platform, we can also use that to generate your embedding. So once we have generated these embeddings, we write this data to Hive. One thing to note here, this is our snapshot pipeline. So that means it will basically take the point-in-time snapshot of the data source. So right now we do not have like a delta or some support, but it takes the snapshot and it will write that data to Hive. And inside Hive, we basically partition this data based on the timestamps. That pretty much means that you have a time series view of your sources. So let's say after certain pipeline run, if you got a bad output or evaluation, you can revert it back to the previous version or previous timestamp. Once the data is ingested into Hive, it goes to the vector database. We support multiple databases. Here right now within Uber we have OpenSearch lives in place, and again the inch blocks corresponding to that are attached later in the presentation. And we will go into more details of what is this index 1, index 2, and index 3 implies. But we basically write all these snapshots to vector database, and then we allow people to retrieve data from these indexes. Once your vector database ingestion is finished, all this information about this pipeline and retrieval is stored in the metadata system. So we have this unified API based, Kubernetes based metadata system, and again, the blog is attached in the references. Now, the next phase is we'll go into more details of once your data is available, how do we retrieve it, how do we manage the versioning, rollback, as well as different type of retrievals. Shivan will go into more details of these. So over to you, Shivan.
Okay, thanks, Divya. So at Uber, we support multiple vector stores, as Divya has mentioned. So both external ones like OpenSearch and internal build systems such as Lucene Plus. So regardless of whether we use an external or internal store, so version control and having the ability to roll back is really important. So in the next 2 pages, I'm going to introduce how we handle dataset versioning for vector stores. So in this page is an example of OpenSearch version control. So OpenSearch is a community-driven open source vector database originated from Elasticsearch, built for search, analytics, and AI use cases at scale. So in OpenSearch, we use an OpenSearch supported feature called alias to manage version control. You can think of an alias as a pointer that refers to a set of indexes. Based on the index timestamp, we can determine which index to query at serving time. So each time we run an ingestion, a new index is created to store a full snapshot of the dataset. After ingestion, the alias is updated to include the latest index, and 2 old indexes are cleaned up by a prune job. So to trigger a rollback, we simply update the timestamp of an older index, since our queries always target the index with the latest timestamp. So when using the OpenSearch for vector datasets, there are both advantages and disadvantages. The main advantage of OpenSearch is its low reliability overhead, because each ingestion simply creates a new index, keeping different versions isolated. So however, the downside is higher cost, since maintaining multiple indexes requires additional storage and resources. Another limitation is that alias is specific to OpenSearch, meaning this feature cannot be used with other vector store systems. Next page, please. So on this page, I'll introduce another mechanism for handling the dataset versioning using Lucene Plus. So Lucene Plus is a Uber Search internal build vector database that leverages the core Lucene features. The key concept for versioning Lucene Plus is the blue-green version control, so which supports 2 approaches. The first one is index level control. Data is ingested into an inactive index, which is then marked as active, while the other index will be deactivated. So this is similar to the OpenSearch alias solution, but we only keep 2 indexes at most, and the version is managed by the version control configuration. Another approach is the column level version control. So a single index will be maintained, but both blue and green versions of columns are ingested into the same index. So column level version control also has its advantages and disadvantages. On the plus side, using column level version control reduces costs, as only one index needs to be maintained instead of multiple ones. On the downside, so it introduces higher reliability overhead. Compared to using separate indexes, column level versioning requires extra caution during ingestion, thorough validation to ensure the data integrity, and has limitation when handling backward incompatible change, such as deleting the index schemas. Next page, please. So on this page, I'll talk more about this high reliability overhead. So I'll walk through the workflow for handling the column level version control. So once the index build is completed, we begin with a completeness validation to verify consistency between the offline Hive table and the newly built online index. Next, we run backward compatible checks to ensure that no columns are missing or removed in the new index. After that, we trigger a non-production deployment to evaluate the index and validate the correctness using some test traffic. If all validation pass successfully, we proceed with the production deployment. Next page, please. After we talk about the dataset versioning, so in this section, I will introduce the dataset metadata. So it is a CRB used to store all of the metadata within the Uber's Michelangelo unified ecosystem. So it is generated by the embedding generation and ingestion pipeline, serving as a bridge between ingestion and retrieval. Dataset metadata also assists on-call engineers in locating relevant details when ingestion or retrieval issues arise. The metadata includes but not limited to the following information. First one is name and namespace, serve as the unique identifiers for each of the use case. Next is online serving information, includes details such as the vector DB cluster, alias, and indices. Hive information refers to the offline table created after embedding generation, which acts as the data source for online ingestion. Embedding information contains the embedding model details, embedding dimensions, and other properties that ensure the consistency between ingestion and retrieval, enable accurate similarity search results. We also provide other metadata, such as the ingestion pipeline and project name. This can help on-call engineers quickly identify the specific project and pipeline involved in an issue. Next page, please. So in this section, I will walk you through the retrieval process. So the process begins when a customer submits a request containing the name, namespace, query, and query filter. The query filter specifies parameters such as the score threshold, the number of documents to retrieve from the vector DB, and any pre-filtering conditions for the search. The retrieval service then reads the corresponding metadata to obtain the serving details such as cluster, alias, and embedding model information. Next, it converts the incoming traffic into embeddings, checks the data version, and sends the embedded query to the appropriate cluster to retrieve the top K results. After obtaining the results, the retrieval service may perform some post-processing steps, such as invoking another large language model to summarize or refine the similarities search results, or pass to the agent module to trigger some follow-up operations. And finally, the response is returned to the customer. Next page, please. So vector stores and similarity search have been widely adopted across multiple Uber projects. One of the largest external use cases is grocery and Uber Eats global search, which significantly improved search accuracy and reduced zero result queries. So beyond customer-facing applications, several internal projects also leverage this technology. A notable example is Uber GenAI on-call copilot, internally known as Genie, which is integrated into a huge number of Slack channels across the whole company to assist teams in troubleshooting and resolving on-call issues more efficiently. In addition to Genie, Uber has developed various agentic applications, such as agents that assist with code reviews, incident root cause analysis, and other operational workflows, further enhancing the productivity and reliability across the whole organizations. Next page, please. So for the future plan, first we want to support the Delta ingestion. As Stevia has mentioned before, currently the ingestion is done in batches using the full snapshot. However, since upstream data source may have only minor changes, Delta ingestion can significantly reduce resources usage and processing time. Second, we aim to support real-time ingestion for vector DB to enable faster data updates and improve freshness. Third, we are focusing on improving the reliability and automated rollback. At present, rollbacks are performed manually, but our goal is to enable automatic rollbacks triggered by any deployment alerts. Next page, please. And here are some reference links. The first one is the Meta Store journey. Palette is the Uber internal feature store. Second one is some link about the GenAI gateway. And third one is the Genie, the on-call copilot tool we have worked on.
Thanks.
I think that's it. Thank you.
Thanks, Divya. It's a fascinating insight into what's happening at Uber. And I think, the unification of all data for AI, whether it's vector embeddings or tabular data and unstructured, I think that's a trend that we'll see more and more of. And I'll take one question from an anonymous attendee. I have an answer for this. I'll throw in my answer and you tell me if I'm wrong. So why do we keep older versions of data based on timestamp, right? If we think about vector embeddings. And one thing I've thought about, what you talked about before, is if, for example, I have evals for my agent where I'd like to, run my evals against my agent and see if the changes improve the agent or not, what happens if your vector store, if the data is updated? Your evals can get worse, but you didn't change anything in the agent. You didn't change anything, just that the entries in your vector store changed. And suddenly your retrieval is returning different rows because it's doing similarity search, but the data is different. And I guess this would really help for that particular problem to do point in time correct. No, cover.
Yeah, that is one of the reasons. So one is that you updated your data and suddenly your agent is performing worse. So we can do a rollback. That is one. A lot of time the data corruption can happen. For example, like someone ran a pipeline which they were not supposed to, or they just updated some sort of bad data. So we wanted some quick way to immediately do a rollback. And the quickest what we can do is we update our alias to point to an older version, and it immediately switched back all the production retrieval to the older version.
Cool. Thanks. There's another interesting question came in here, which is maybe you can give an idea of the percentage of your feature vector embeddings that are used for similarity search versus model features as input to model features. And then the second part was, and this is an interesting one, if you're retraining the vector embedding models themselves, the data they generate the vector embeddings they generate will maybe not be compatible with the existing ones. So how do you handle that and the versioning issue there?
So on the first part, I think right now we have almost 90:10 ratio. So 90% applications are generative AI used primarily for RAG applications, and almost 10% use cases which we have semantic search, our ranking and recommendation models are using them as a features. So we would probably, I think we are now started expanding to use it more in the core ML aspects as well. So hopefully in future we'll expand, or maybe that ratio can change. I did not get your second question. Can you repeat?
Just unmute myself here. Sorry. No, the second part of the question was, so, how do you handle, I mean, you did talk about versioning, right? But I mean, I guess it's the linking of versioning between training and serving is, I guess, the issue there. That, I've created maybe you train custom vector embedding models. And if they're updated daily, then the embeddings they compute may not be compatible with the embeddings that are already in the vector store. And how do you handle that particular
Oh, I see.
set of updates?
So when this pipeline runs, the batch pipeline, we create an immutable metadata. So your model is basically fixed. You cannot really update it for the existing data set. If you want to update your embedding model, you would have to create a new pipeline or your new data set. So that way we make sure that people do not mistakenly change something which they are not supposed to.
Great.
So that's pretty much, we also have this, so this pipeline, I think we did not go into the details, but what you can do is you can define multiple models. If you, let's say, a lot of time what happens is you don't know what is going to work best, so you may want to experiment with different models. So you can create experimentation pipeline where you can define multiple models. And what we do is we use the source data, and corresponding to each model, we will generate different set of embeddings. And given in OpenSearch, you can have different columns with different dimensions. It allows a lot of flexibility. And then this column kind of works as a feature we have in feature store. So you can just access different features with different models, but the name of each feature would be different, so they are isolated.
All right, very good. I have a question about real-time ingestion, I think, which Jan had as future work. Now, we also provide OpenSearch as the vector store in OpsWorks. It's the vector index. And one of the things that we notice about it, at least, is, for real-time ingestion, you really need to do batch updates. And, How's your thinking with regard to, keeping the freshness of these vector embeddings as minimal as possible? Because, a vector embedding store is not like a key value store or RonDB where we can do millions of reads and writes per second. You have to balance reads and writes. So writes are not as good as maybe for frequency compared to reads.
Right. So I think the use case for the real-time ingestion for us is primarily related to context engineering. So a lot of time in your RAG applications, people get certain information which they want to immediately ingest. And our batch pipeline, it can actually run at a very high frequency. So there can be three cases. One is the batch, which runs daily, then absolute real time, which is almost as near real time, like within minutes or seconds of latency. And the third can be the micro batching. So our existing batch pipeline, we have cases where people run it every hour. So based on, I think, where your use case fit, that's where we kind of provide the balance. Like you can either use micro batching if you are okay with hourly updates, or you can do near real time, but then yes, you would have to, based on the resources available, may have latency and other indexing issues.
Brilliant. Thanks, Divya. Thanks, Joanne. We're out of time. We're going to have a quick break.